Okay, in this video, we're going to talk about the first section of Chapter 2. Chapter 2 is on applications of integrals. I think the book actually calls it applications of integration, but minor difference. So the first section is on areas between curves, and we're going to briefly review some concepts we talked about in the video on 1.3 on Riemann sums. As I said then, that concept gets used a lot in this chapter 2. So let's just review that briefly. If this is at all confusing, you might want to go rewatch that video. So let's say we have some function f of x, right, and it's continuous on some interval from a to b, and I want to find this area, right? So in order to do that, I'm going to subdivide my interval from a to b into subintervals. I'll be cutting it at x1, x2, x3, and so forth, and I'll be forming rectangles. And I guess I'm doing an underestimate in this example of the area. And if I have my generic rectangle somewhere in the middle, this is rectangle I, right? R subscript I. And let me change colors here. And the width is going to be, well, what's the width of that subinterval? Well, that's going to be delta x, or in other words, b minus a over n for all of these, right? So delta x, change the stylus size. So delta x, which is b minus a over n, right? Typically. It doesn't have to be, but typically is what we'll be doing. That's the width. Now, since I'm using the right edge in this diagram to make the height of the rectangle, then that coordinate xi star, or if you want ci is what I would typically do, but the book uses xi star. That's going to be used to form the height. So this point here at the top of the top right corner of the rectangle, well, that's formed using the function so that the rectangle touches the function. So that height is f of xi star. F of xi star. Okay. As something we've said before is that this xi really could be anywhere in the interval. The height, there's options on how you make the height. It ultimately does not matter conceptually, but we will typically use the right or left edge just because that's easier. For some functions, you have to use the middle because that's the way you make the algebra go. So the area of rectangle I, well, that's going to be the height, f of xi star, times the width, delta x, right? And if you want the area of all the rectangles, so the area estimate, in other words, the lower Riemann sum, in this case lower because the rectangle's under, well, this is going to be the sum as I goes from 1 to n, the number of rectangles of f of xi, xi star, delta x, okay? And then you would just go work out whatever that sum is, how does the algebra work out? We did examples of that in the video on 1.3. So there's finding the area under a graph. What if I don't want to talk about the subintervals anymore? I don't want to really build the Riemann sum and do all the algebra. I just want to consider, well, how do I build the integral, right? The width we're going to call dx rather than delta x. This is something that we talked about in, at least somewhat in the video 1.3. So the height is just f of x. Instead of identifying that place where we're making the height of the rectangle as xi star, we'll just call it some x coordinate. We don't need to give it a special name. So that the height is f of x. Okay. So the area of just that generic rectangle somewhere in the middle, well, this is just f of x, the height, times dx, right? Dx playing the role of delta x. It's in principle the same thing. The differential is a small slice of, and there's a technical difference, but for us, in principle, it's the same thing. It's a small slice of the x coordinate or the x variable. So if I want to have all those rectangles, well, I have to add them up. Well, that means I want the integral, and this is because of the word sum. It's a stretched s. That's what the symbol is. It's a stretched s. We're summing from a to b of f of x dx. So this notation gets used because it mirrors you can see the next example. It mirrors the Riemann sum notation. You know, the summation symbol. I know this is kind of zoomed out, but I need to show both. The summation symbol is mirrored with the integration symbol. The f of xi star is mirrored with just f of x. And the delta x is mirrored with dx. Okay, so it's the same arrangement of objects, I guess, if you want. The first thing tells you, okay, we're doing a sum. The second thing tells you, here's the height. The second thing tells you, here's the width, basically. If you're a math major and you go take real analysis at some point, you'll get a lot more detail on this. I'm glossing over some things, of course. So what if I have a function that dips below the x-axis? The graph is not entirely above the x-axis. So if I'm finding the area, I have to be careful, because this section right here, being below the x-axis, will get counted negatively. This is something we talked about previously when we talked about total area. And that was, I'm sorry, that would be in Cal 1, rather. This is covered in Cal 1 towards the very end of the course. You find total area between a function and an axis. So if I fill these in, I'll try to do it as expertly as possible. I really could have colored these in ahead of time. The other ones are mostly colored in ahead of time, but this one I wanted to do on the spot. So I'm marking in blue the regions where the graph is positive, has positive values, because that's where the heights will be measured positively. And then I'm marking in red or pink where the graph dips below the x-axis, because that is where the rectangles will be, the heights will be measured negatively, okay? Because if I go and make my rectangle, my generic rectangle, and maybe the rectangle tool will work with me. Yeah, good enough. Good enough. I'd like to get rid of that spot, but oh well, I'm not going to fiddle with it. If I just call this position here x, it's some x coordinate, right? Then this height here, this is f of x, right? So I've drawn my generic rectangle. I don't have subintervals. I don't have x1, x2, just some generic rectangle. I'm representing one somewhere in the middle. So the area of this is going to be the integral from a to, well, a to someplace. I've marked a and b. Let's call this one c and call this one d. The letters don't really matter. I can call them whatever. So this first section, this will be the integral from a to c of f of x dx. Okay. So that part's straightforward. It's very much like this one worked out. Now if I get to the next region and I go to make a rectangle here, and again, maybe the auto rectangle tool. Yeah, let's call that good enough. So let's say right here, this is an x coordinate. It's not the same one as this one, but we're in a different region, so I'm not going to worry about it. And this height here, this is, well, f of x gives you the y coordinate of this point down here, right? What's the height level of the function? But of course it's negative. So f of x times delta, or dx rather, in this case, this is not going to give me the area. It will give me the negative of the area, right? Because the function's below the height of a rectangle. Height is positive, right? But since I'm measuring below the x-axis, the function's producing a negative value. So this area here, this will be the integral from c to d of the negative of f of x dx, okay? And then, I guess I don't need that anymore. And then this section here, if I go to make a rectangle, interesting. Well, we'll just do that then. So we'll call this is x, and I didn't label the dx's on these. Dx is the width, right? And then the height, this is f of x. So this area is the integral from d to b of f of x dx. Right? And then I can add up those three different integrals to get the total area. Right? This one we talked, or not we, but was talked about in Cal 1. Okay, so let's talk about the next concept, this is all Cal 1, right? This is Riemann sums and areas between either under a function or between a function and the x-axis. It's all Cal 1 stuff. So this is just review. So now, what about if you had two functions and you want the area between them? And I guess I'm going to be a little sloppy with the shading because I don't want to take forever. Okay, you know what? Let us do this. It's not going to be neat, but I really should have highlighted this one ahead of time. Oh well. Let's pretend I'm doing this really well. If you squint, maybe it'll look okay. Okay, so there we go. We want that area, right? So when I go to find this rectangle, well, I'm not going to even be touching the x-axis because that's my region is up here, right? So when I go and I make my rectangle, and again, we'll see if the auto rectangle tool will. That's pretty good. We'll say that this position here, this is x. The width, it's kind of hard to see because of the graph, the thickness of the graph that I had pre-drawn is it's kind of thick. It's hard to see the bottom of the rectangle, but that's dx. That's the width, right? Now this height level right here, is that f? Yeah, f is the top function. This guy is x comma f of x, right? Make some good parentheses, and then this point here, well, this is x comma g of x, right? Those are the two height levels. So the height of the rectangle, this is f of x, and that's not a minus sign. Sorry, let's do this. This is f of x minus g of x. Okay. So another way to think about it is, if you wanted, you could say, oh, well, I'm going to take, try to draw it a little bit better. I'm going to take this big rectangle, right? And then I'm going to take this rectangle and then chop it off. So I'm subtracting the height to get the height of just the intervening height between the two functions, right? Or the way that I drew it originally, that from one corner to the next, you're going from g up to f. So the height would be f of x minus g of x. So the area of this rectangle is f of x. Actually, you know what? I think I'm supposed to have it down here. Yeah. F of x minus g of x dx. Okay. And again, we don't have a number for dx, right? It's a differential. So I'm representing the structure of the Riemann sum without having to go through the trouble of the subintervals and the i's and b minus a over n and all of that. Okay. So the area will be the integral from a to b of f of x minus g of x dx. All right. Another way to think about that, along the lines of that alternate rectangle I talked about, is you could say, well, what I want to do is I'm going to find the area under f, all of this down to the axis, right? Pretend I highlight that really well. And then I'm going to find the area under g down to the axis, right, between the axis and the function, and subtract those things. So auto line tool is trying to help out. So of course, this equals the integral from a to b of f of x dx minus the integral from a to b of g of x dx. If you just use the difference rule for definite integrals, which is inherited from the difference rule for antiderivatives. So let's do an example. I've got two functions here. I've got sine and cosine. You might recognize them. And I want to find the area of that blue or teal highlighted region. Okay, so the blue function is cosine, the green function is sine. In fact, let's label these. Let's say this guy, right? This is, say, y equals cosine of x, and then this one here, this is y equals sine of x. Okay. Maybe on your screen the colors don't look that different. So I want this. I want this area. How do I do it? Well, I can either think of this as being a formula. That's one way to do it. I don't like memorizing formulas. I really prefer to draw things out and think conceptually and try to develop an understanding of which things to combine, which things to subtract, and so forth to get the region that I want, the total. Okay. You certainly can try to memorize formulas, and maybe that's more effective for some people. But to me, it just doesn't work very well for me. Okay, so what I'm going to do is say, well, I'm going to start by building my rectangle, and I'm not going to assume that the auto rectangle tool is going to play nice. So I'm going to use the auto straight line tool. With mixed success. Maybe I'll just freehand that last one. Okay, good enough. So there's a rectangle that fits inside the region. And if I were to go do one over here, right, I could have one there, or I could have one over here, right? But I'm just doing one generic one so I can get the concept of what am I subtracting, what am I adding. So of course the width, this is dx, right? Now the height is from this corner down to, and you know what? I kind of have it's not a mistake per se. It's not super important, but let me do this. I really ought to be using the same left or right only and not switching sides. So as you probably covered when you talked about Riemann sums in Cal 1, if you have a little bit under or a little bit over, like if you focus on the bottom here, oh, we've got some missing area we're not going to catch, right? And up here we got some extra area we're going to catch. It's an estimate. That ultimately doesn't matter because, as n goes to infinity, you have infinitely many thin rectangles. Then the extra bits that are missing or extra count, the missing or extra, doesn't matter, right? It shrinks to 0. So, but I need to use either the left side or right side only to make my diagram make more sense. I don't want to be switching sides. Wait, if you said, because what I was about to do is say, oh, this is where x is this point here, but then I would have to, for the other side, go, oh, well, x is here. Yeah, it's not super important. I could do that and the algebra would work out fine, but it would just look really weird. So what is the height of my rectangle? Well, it's the top, whatever that function is, which is sine in this case, minus the bottom, cosine in this case. Always top minus bottom gets you the intervening region, okay? So while my width is dx, my height is sine of x minus cosine of x. Okay, so that's going to be how I set up my integral. I'm going to have the height times the width, right? I'm also going to need to know, well, what are these intersection points? Because I'm going to need to, integrate from somewhere to somewhere. I need to know the interval I'm dealing with. And you might be able to tell just from the way I've drawn it that this point right here, that this is pi over 4. And this point right here, this one is 5 pi over 4. Yeah, I believe that's correct. 5 pi over 4. If you're, if you have a really good diagram, you just look at it and maybe you could tell. If you're not sure, the way I would do this is say, well, let me set the two functions equal to each other. Sine x equals, equals cosine x, right? To see where do these, where do these two functions agree? And I would solve that equation. However, you might look at this and go, oh, I'm not sure how to solve that. If you think about the unit circle, where are sine and cosine the same? Well, in the unit circle, which we're going to have to think about from time to time, the auto circle tool is problematic. Okay, there we go. If I draw a unit circle out, try to make it reasonably accurate. Okay, so sine and cosine are equal right here, right? They're both root 2 over 2 on the unit circle. And then also over here, they're both negative root 2 over 2. Well, what angle is that, right? This is pi over 4. And then this angle here, right? This is 5 pi over 4. Right? So that's one way to do it. Just think about the unit circle. Another way is to take the equation and divide by cosine on both sides. So you'll have tangent theta, or tangent x rather, equals 1. Well, when does tangent, when's the output 1? You just think about the unit circle and you end up doing the same thing. Really. So there's a couple ways to deal with that. And so you will typically, I want to say you often, I don't know about typically, often homework, tests, stuff like that, you won't be given a diagram. Sometimes you will, sometimes you won't. It depends. So you need to be prepared to find out your limits of integration by finding out where do these things intersect. And I think later on we might have an example where you have to figure that out. I mean, the diagram shows it, but it's not necessarily so clear. I think there's one later like that. So I want the integral from the starting point to the stopping point. Right, those two numbers I just found of height times the width. Okay, so I've done all the setup. This is my integral, and now the rest is really a Cal 1 thing. Now that I've figured this out, right? I've built the integral. That's the Cal 2 part. That's the part we're learning in this section. And then the rest is really Cal 1. But we'll go ahead and do it. It certainly does not hurt to see more examples of this. If this is totally easy for you, you might want to skip ahead a little bit. So I'm going to find my antiderivative. Well, my antiderivative of sine, well, that's going to be a negative cosine, right? Minus the antiderivative of cosine will be sine. Right? And I'm evaluating at pi over 4 and 5 pi over 4. I have to remind myself to not try to write quickly because my handwriting gets really bad when I try to write quickly. So negative cosine of 5 pi over 4 minus sine of 5 pi over 4. And then minus negative cosine of pi over 4 minus sine of pi over 4. And of course, this minus sign here is going to cancel when I distribute it. It will cancel the other two. So really, this is all plus cosine pi over 4 plus sine pi over 4. And of course, the trig function values we just talked about, cosine of 5 pi over 4 is negative root 2 over 2, but I'm negating that, so this is really root 2 over 2. So I'm going to get root 2 over 2 minus negative, but so really plus root 2 over 2. Minus negative, so really plus root 2 over 2, and then double negative root 2 over 2. So you add all that up, you get basically 2 root 2 over 2. I'm sorry, 2 root 2 rather. 2 root 2. Either you can say, well, I have 4 root 2 over 2 and then reduce it, or you can say, well, if you add half a thing with another half of that thing, you just get the thing. So root 2 plus root 2, you get 2 root 2. Anyway, so maybe that part was easy. Maybe that was trivial for you. So the key part is building the antiderivative, the integral, the definite integral that you want to get the area that you need. Now there's other things we could do. There's variations on this, but I think we'll leave that for another time or another example. But I want to point out one thing. What if really I wanted more area? What if I didn't just want that part that's already highlighted? What if I also wanted this over here? Right, we'll pretend I'm shading this really carefully and neatly. How would I do that? Right, and you just set up a new integral, right? Now, when I go to make my rectangle, I have to be careful because the functions have sort of switched positions. Now cosine is the top function. That's never going to be quite straight, so I'll just freehand that. Good enough. So of course the width is dx, right? But now cosine is the top function. This point right here, the height level is cosine x, this one is sine x. So the height of my function, or sorry, the height of my rectangle rather, this is cosine x minus sine x. So if you want to build that integral, well, you got to switch it around, right? Now you're probably thinking, why are you doing that? Why are you making things difficult? So half of you are probably saying, why don't we just double the area we already found, right? Because it's symmetrical, it's a mirror image. So if we wanted both of them, well, I would just do 2 times the integral from pi over 4 to 5 pi over 4 of sine x minus cosine x dx. Okay, you don't need to do all that work. You can just double it. Oh, well, then that's going to be what? 4 root 2, right? Easy. Not a whole lot of work to do. Okay, so that's that example. So let's move on to the next one. What if I wanted the area between an exponential function and a quadratic function? So y equals 2 to the x and y equals x squared. I've drawn a reasonably good freehand sketch just because this one you got to be kind of careful with. It's kind of a pain, and I didn't want to try to do it, on the fly. That would have gone poorly. So you can probably tell from the graph, well, these cross twice, right? Right there and right there. But what values are those, right? We're going to have to do this integral in pieces because I want to find the area between the two graphs, and I've got 3 regions, right? And which function is the top function? The top makes, it forms the top end of our rectangle that switches, right? So how are we going to figure that out? Well, as I said earlier, well, you just set the two functions equal to each other and see what you get. So if I do 2 to the x equals x squared, you can see pretty quickly that that might be a challenge. This is what's often called a non-algebraic function. It's not so clear how to solve this, but if you just think about it, well, basically with this kind of problem, this kind of equation, you can use guess and check. Now there is a method called Newton's method that is covered in the OpenStax book. You may have seen this, either it was covered in Cal 1 or maybe you just happened to notice it and you read it. So there are methods for solving this kind of equation. But since not necessarily everyone in Cal 1 covers this, when I teach Cal 1, we don't have time for this typically. I would like to, but there's no time. So I'm going to assume that you guys haven't seen that. So we'll go to guess and check, even though there are technically methods that we could employ. So if you just look at it, you might notice, well, 2 squared equals 2 squared, right? Yeah, just plug in 2. And then also 2 to the 4th, this equals 4 squared. So just by guessing and checking, 2 and 4, those are our solutions. Okay, typically we don't want to rely on guessing and checking. Sorry, struggling with the interface there. Typically, we don't want to rely on guessing and checking, but in this case, we kind of have to with this example. Since we don't know, we either we don't or we'll pretend we don't know Newton's method. So that means that right here, this is 2, this one's 4, and we're finding the area on the interval from 0 to 5, right? So now I can set up my integrals. So my first integral for this first region will be the integral from 0 to 2, and I just need to set up the difference of the two functions, top function minus bottom function. I don't have to draw the rectangles every time. And in particular with this one, because that's such a tiny little sliver, do I really want to get in there and draw a rectangle? Not really. What matters is top minus bottom. So as long as you identify, well, this top function, this is the exponential 2 to the x. And this bottom function, this is the parabola x squared. So my first region, this will be the integral from 0 to 2 of 2 to the x minus x squared dx, okay, plus the next region will be the integral from 2 to 4. And then here, it's actually the parabola that forms the top of the region and the exponential that forms the bottom of the region. So I got to switch the order in my integrand. So this will be the integral from x squared. I'm sorry, not from, but of x squared minus 2 to the x dx, and then plus the last interval 4 to 5, and the 5 is, remember, from the problem, the statement of the problem. So this will be the same as the first integrand because it switches back. So 2 to the x minus x squared dx. You won't necessarily always have it to where the third one and the first one are the same. That will sometimes happen, but not always. It depends. So don't just assume that. So like I said earlier, once we set up the integrals, the rest is kind of Cal 1, but it doesn't hurt to see it again. So this one, this will be 2 to the x over ln. 2 is the antiderivative minus x cubed over 3. Evaluate at 0 and at 2. Plus x cubed over 3 minus 2 to the x over ln 2. Evaluate at 2 and 4. Plus the antiderivative here will again be 2 to the x over ln 2 minus x cubed over 3. Evaluate at 4 and at 5. Okay, so now I can evaluate, if I can zoom in a little bit. So this will be, well, 2 squared is 4 over ln 2 minus 8 thirds minus, so 2 to the 0, that's 1, so 1 over ln 2 minus 0, right? Plus 4 cubed, that's 64, I believe, 64 over 3, minus 16, yeah, 16 over ln of 2, minus, I plug in 2, that'll be 8/3, minus 16 over ln of 2. Is that right? No, 4. 4 over ln of 2. Okay, plus, oh yeah, sorry, 2 to the 5th, that's going to be 32 over ln of 2. Sorry, I started wondering if I'd made a mistake earlier. Hopefully not. And then 64. I'm sorry, 125 over 3. Minus. That's going to be 16 over ln of 2. Yeah. Minus 64 over 3. Okay, so got a lot of numbers here. So I'm going to resolve all of the parentheses. I'll distribute all of these minus signs. So I will get 4 ln of 2. And probably I'm going to zoom in for now. Otherwise, it's just going to be really hard to see this in the video. Minus 8/3 minus 1 over ln of 2. Of course, I'll be combining like terms shortly. Plus 0 plus 64 over 3 minus 16 over ln of 2 minus 8/3 plus 4 over ln 2 plus 32 over ln of 2 minus 125. I started getting worried that I had forgotten a minus sign. 125 over 3 minus 16 over ln of 2 plus 64 over 3. Okay, so when I total all that up, I'm going to have 4 minus 1, so 3, minus 16 is negative 13, minus 9, 23, so 7 ln over 2. And then negative 3, 56, 48, well, 112, minus 13, negative 13 over 3. I believe that's correct. Let's go with that. And if there's a minor error, well, I'll probably hear about that later. So there we go. Again, the beginning, the setup. This is really the Cal 2 part, and then the rest may be routine for you, maybe not. And if not, then it will become routine, within a few weeks of doing more of these. Okay, so that was an example of doing that. So there are more. So let's go to the next one. Or next concept, actually. So what if we had a more complex area with multiple functions going on? So if we have a region like this, and I want to do vertically aligned rectangles like we've been doing, it's the same thing. F of x minus g of x is the height. It's just that when you're over here on this other side, maybe this one's going to be, say, h of x minus g of x, right? Because it's the upper portion, the upper boundary is made up by a different function than it was on the other side, right? So you have to do 2 integrals to get the area because there's a corner here, right? Now you can also do horizontally aligned rectangles. Sometimes that's going to be really useful. It depends on the problem. For area between 2 curves or between multiple curves, later we're going to need to do this approach regularly. So this is why one of the reasons we're doing it now, so that when we use it repeatedly later, it'll be familiar by then. So if I make my rectangle this way, then the width of it is the long side and the height is the short side. And we're going to say that I'm going to say the height or thickness is dy. It's a slice of the vertical axis, the vertical coordinate. And then the length or width, however you want to describe it, that's going to be a difference of two functions of the y coordinate. Okay, and of course we'll do examples of this. I just want to show you a quick diagram of we're going to be doing two different approaches. So let's start with this one, doing the way we've been doing it, where we have the vertically aligned rectangle. Okay, so we're going to find the area under both of these functions from, I guess that's 0 to 2. Yeah, this is 2 right here. Okay, so when I go to do that, because I've got two functions, for part of the interval, I'm going to have the top of the region is made by this parabola. For the other part of the interval, the top of the region is made by this linear function. So I'm going to have two integrals. Okay, so the place where they cross there is, I'm pretty sure it's 1. Yeah, it's 1. So this first integral, I'm going to build the rectangle. Its height, let me make that a little bit neater. Its width, of course, is dx, right? And its height, this is going to be x squared, right? For the other side, the width, of course, is still dx, right? But the height, this is going to be 2 minus x, right? And of course, you might say, why are we even doing an integral? It's just a triangle. Well, yeah, but we're choosing a simple example to see how it goes before we try to go to doing harder functions in a new concept. So my integrals are going to be like these. I'm going to have the integral from 0 to 1 of x squared dx. Right? This is the height of that rectangle times the width of that rectangle. Okay. Plus the integral from 1 to 2 of 2 minus x. Sorry if I can make parentheses. Dx. Okay. This is the height of the other rectangle times its width. Okay. So then, maybe this is an easy antiderivative to do, or two antiderivatives really. So we'll have a x cubed over 3, evaluated at 0 and at 1. That one's going to be easy. And then we're going to add to that the, what is that going to be? 2x minus x squared over 2, evaluated at 1 and at 2. Right? That will also be relatively simple. So we're going to have 1/3 minus 0, right? Plus 4 minus 2, right? Minus 2 minus 1/2, right? So we have 1/3 plus 2 minus 3/2, I believe. And of course, 2 minus 3/2 is 1/2. 1/2 plus 1/3 is 5/6. Okay, so we get 5/6. So that's that area using two vertically aligned rectangles, and we had to do two of them because there's two different top functions depending on where in the interval you are. So now, when I go to do my next example, I'm going to use dy instead. I'm going to have a horizontally aligned rectangle. Okay, so let's draw that rectangle, and maybe the auto rectangle tool will work. Yeah, let's say that worked. Okay. Maybe it's too thick. Maybe I should make it shorter. Can I do that? Yeah. Okay. Awesome. There we go. Okay. So we're going to say that this height level is y. Y is the height at which the top of the rectangle rests. Okay. The height of that rectangle is dy, the differential of the y coordinate. It's a slice of the vertical coordinate. Okay. It's like think like you have a piece of cheese and you're slicing off the top, right? You got a piece of cheese and you cut across, you cut the corner off, and you got a flat little plane. You make another cut, you can peel off a piece of cheese, right? That's the visual I like to have because cheese is awesome, right? So, what about the length or width in this case, if you want? radius of 1. How do we find that, right? Well, what I need to know is I need to know this x coordinate as a function of y, and this x coordinate as a function of y. If I subtract them, well, then I'll get the intervening distance, right? So I need to take this function here and rewrite it not with y as a function of x, but x as a function of y. And I need to take this function here and rewrite it not with y as a function of x, but x as a function of y. I need to invert the two functions, essentially, is what I'm doing, okay? So, got my two functions here. F of x equals x squared, which I'm going to rewrite as y equals x squared. And I'm going to solve for x. I'm going to get x by itself. So I'm going to apply the square root function to both sides. As we've probably talked about before, when you apply the square root to a square, right? The square root of x squared is not just x; it's the absolute value. However, we're in quadrant 1, right? I can't slide over anymore. We're in quadrant 1. We only have positive values. There are no negative coordinates here, so x is positive regardless, just like y is positive in quadrant 1. Although I guess for parabola, y is always positive or 0. No negative coordinates at all. We're in quadrant 1. So this is my x coordinate as a function of y. So right here, this guy here, this is the square root of y. Should probably change one stylus size down. That's the square root of y, okay? So now we can do the other one. Sorry, struggling with the interface here. So I'm going to write this as y equals 2 minus x, and I, again, will solve for x, get x by itself. So add x to both sides. The order in which I do this isn't super important. I'm just choosing to do it this way. Then I can subtract y on both sides, and I get x equals 2 minus y. So that is the other x coordinate as a function of y. 2, oops, that's right. I had changed the stylus size. 2 minus y. So that means that the length equals 2 minus y minus the square root of y. There's my length function. So the area of this rectangle, length times width, base times height, I guess, whatever you want to call it, it would be dy times, height times width would be dy times 2 minus y minus the square root of y. But I'm going to change the order. I'm going to put the dy at the end because that's what we typically do, in our integrals. It's not incorrect to put dy at the beginning. It's just we typically put it at the end. It's a product. You change the order of a product, it doesn't affect the result because of the commutativity of multiplication. So there we go. That's the area of a generic rectangle somewhere in the region. So now what I have to do is figure, okay, what are my limits of integration? Where am I integrating? From where to where? So I want to think about if I take this rectangle and slide it all the way down to the bottom, it's going to be down here, right? What is that y coordinate? What's the height level? Well, that would be 0. You're on the axis. Then I'm going to think about sliding this rectangle all the way to the top. It's going to shrink when it does that, of course. So I've got the rectangle. It's going to be tiny. I'm going to change colors here so you can see. It's going to be tiny, but it's going to be like right here, right? Little tiny rectangle in the corner there. Well, what is the height level? What's that y coordinate? Well, that's going to be 1. It might be obvious from looking at the graph, maybe, or looking at the functions involved, and especially if you scroll up. This right here, x equals 1, the y coordinate. You plug 1 into either of the functions, you get 1 as the y coordinate. So 1 is our y coordinate. Okay, so change colors here. So that's 1. So I integrate from 0 to 1. So I'm going to do the integral from 0 to 1 of, it's really tiny, so I'm going to write it big again, of course, 2 minus y minus, and I'm going to write this with an exponent rather than a root, just because, power rule for antiderivatives. There we go, the integral from 0 to 1 of 2 minus y to the 1/2 power dy. That integral is going to calculate the same area as this one. It's just set up differently. But we're going to get 5/6, as you'll see in a moment. We'll get the same answer, unless I've made a mistake somewhere, of course. So this will be 2y minus y squared over, I'm going to change to a thinner stylus. That's a bit much. So 2y minus y squared over 2 minus 2/3 y to the 3/2 power. I believe that's correct. Yeah, let's get 0, 1. So we're going to have 2 minus 1/2 minus 2/3 minus 0, right? So 2 minus 1/2 would be 3/2, 3/2. And I won't cut corners here. I'll work all this one out. Just because I don't want anyone to think I'm just asserting that the result is the same as the previous one. So common denominator of 6. So 9 over 6 minus 4 over 6. We get 5 over 6. So of course we get the same result. So sometimes this is easier. You'll notice this one, there's only one integral. This one required 2 separate integrals, 2 antiderivatives. Ultimately, it was 3 terms that we had to deal with, right? There are 3 terms. Here's also 3 terms. So did it really save us? Sorry, did it really save us any time? Well, maybe not. Not in this example. This is a really basic example. But there will be some problems for which this won't work. You kind of are stuck with doing horizontally aligned rectangles. Sometimes you'll have that. There'll be other kinds of problems where you end up needing to do both ultimately. When we get into some application problems, just a quick preview. For example, if we wanted to find the geometric center, like in a circle, the center is the center, right? In a square, the center is the center. But if you have a region like this, where's the center? How do you calculate that? That in those cases, we're going to need to do both vertically and horizontally aligned rectangles. Anyway, so that's that example, but we've got more. So this video, I'm not sure how long it's going to take. I generally try to make these about 90 minutes or less. And we're about the halfway point. So yeah, I think it's not going to take the full 90 minutes that I typically would expect. I don't think this is our last example. It is our last example. Okay, so maybe the whole thing is going to be like 70 minutes or so. So now we're going to find the area of this region that's bounded by 3 functions. We've got, well, I say functions. I'll clarify in a second. So we got y equals x plus 1. That is this guy here, right? Slope 1, straight line. Y equals negative x minus 1. Right? So that is this one right here. Slope negative 1, straight line. And then those are both functions, of course. And then x equals 2 minus y squared. That's this sideways looking parabola. So this is not a function in the usual sense. Y is not a function of x. It fails the vertical line test. But it is a function in the sense of x is a function of y. Okay. So when you have that, if I go to try to make, there's 2 basic ways to do this. I can make vertically aligned rectangles, and I can make horizontally aligned rectangles, right? And in fact, I'm going to do, before we get even going any further, I'm going to copy this because I might decide to do 2 different methods, and I don't have to redraw it. That took a while to draw, so I'm going to take this, just save a copy down there. Okay. So you might also notice, and I think this is what we're going to do. We're going to utilize this, that this top half is identical to this bottom half. The one's a mirror image of the other, right? So if I were to do horizontally aligned rectangles like this, I would only have to integrate along this component of the y-axis from 0 to wherever that is that we'll find in a few minutes. Okay. If I were to use vertically aligned, well, then I don't need my rectangle to go all the way to the bottom. I just need my rectangle to go to the axis, integrate from -1, I guess, to -2. I'm sorry, to +2, rather. Integrate on the x-axis, and then double the result, right? So I can utilize the symmetry. I can pick vertical versus horizontal. So, I guess we will do both in this one. So let's go ahead and do vertically aligned first. Now, if I'm doing vertically aligned, because there are two functions here that form the top of the region when I'm doing vertically aligned, I'm going to have 2 different rectangles I have to set up. So this is a lot like the earlier example that we did. So when I go to do this one, and I guess I'll put it here, right? There's a rectangle. And I will label, here's dx. And then the height, well, this is going to be whatever that function is, y equals x plus 1. So x plus 1 is the height. When I go to do my rectangle over here, pretend I drew that really well. The width, of course, is dx. And then the height, well, this is going to be, well, what is it? What is the height as a function of x? Well, that means we need to take our function, where is it? X equals 2 minus y squared. Because what this one does is it gives me x as a function of y. But in order to make this height, I need y as a function of x. And I'm in quadrant 1, right? All of this is in quadrant 1. So I don't have to worry about any minus signs. So I will add a y squared to both sides. So x equals, I'm sorry, yeah, x plus y squared equals 2. Subtract x. Y squared equals 2 minus x. And then y equals the square root of 2 minus x. Again, since we're in quadrant 1, I don't have to worry about minus signs. Everything's positive, right? Or in other words, the x coordinate maxes out at 2, and so you never run into square root of a negative. Is another thing to consider. Okay, so this is going to be the square root of 2 minus x. That's the height of that rectangle. So now I'm ready to set up my integrals and get the top half, and then I can double it at the end to get the area. Okay, so I'm going to say from the beginning, and we have 2 times the integral from -1 to 0. Oh yeah, almost forgot. Where does that happen? Where do they cross? Well, let us deal with that. So I guess I will put it here. I want to see where does this linear function cross this parabolic function. So I've got y equals x plus 1 and x equals 2 minus y squared. And there's a couple of ways to do this. I think maybe substitution might be the best. I'm going to take this 2 minus y squared and plug it into that equation for x, because x is 2 minus y squared. So I'm going to have y equals 2 minus y squared plus 1. I'm going to subtract y on both sides. 0 equals, and combine like terms as well, 3 minus y squared. And probably this is going to factor. Yeah, I think I chose this so it factors in a relatively easy way. I'm hoping. No, it doesn't factor. Oh, no, it doesn't. Okay, well, what I'm going to do is this. I'm going to multiply both sides by -1. Y squared plus y minus 3. So we're going to have to use a quadratic formula or completing the square for this. I'll use quadratic formula. So y equals -b plus or minus the square root b squared minus 4ac all over 2a, right? This is going to get a bit messy, and I hope. Yeah, I was worried I was making a mistake, but if you look at this is where 1 is, so this is definitely not a whole number. I hope I'm not making an error, but I don't think that I am. So -1 plus or minus the square root of 1 squared, which is 1. Well, -1 squared, which is 1 squared, which is 1, minus 4 times a times c. Well, a is 1, c is -3, so that's going to be -4 times -3, so plus 12 all over 2. So this is going to be -1 plus or minus the square root of 13 over 12. Okay. Now, of course, I'm solving for y. I got a y coordinate, but I want an x coordinate, right? Well, since I'm in quadrant 1, I know I'm taking positive values only. So I'm going to go here and first get rid of the minuses, because I know I don't need those. So -1 plus root 13 over 2, or in other words, root 13 minus 1 over 2. But I need an x coordinate. Well, take this guy, plug that in. So And you're probably starting to notice, this is getting to be a real pain. Maybe I don't want to do it this way, but we're going to keep going. But when you pick one method over the other, you might realize this is not going the way I was hoping. All right, this is getting really kind of messy. We have a lot of messy numbers, and they're going to get a bit worse. But we'll keep going, and you'll see in the next version, maybe it's easier when we use the horizontally aligned rectangles. So that's going to be a 2 minus, because of this function here, right? X equals 2 minus y squared. 2 minus the square root of 13 minus 1 over 2. And this is really squared, right? This is really getting to be a pain, but we'll keep at it. So 2 minus 13 minus 2 root 13 plus 1 all over 2. And of course, this 4, I'm going to write that as, this 2, I'm going to write as 4 over 2, because I want to combine like terms. So we are going to have 18 minus 2 root 13 over 2. Reduce that, 9 minus root 13. So we have a very messy number, but that is where the limit of integration is. All right, and you might be thinking, well, if the other way is easier, why don't we just give up and do the other one? Which, like on a test, do that. Stop here, like make a note, still turn it in. Say, this is not how it's supposed to go. I'm going to try the other method. Turn that in as well. But you switch the other method if you feel like this is not the right way to do it. This method is not working very well. It's getting really messy. You can always, it's okay to switch mid-problem, switch to a different method. That's totally fine. So that's, again, going to be, this is my top function, x plus 1 dx plus the integral of 9 minus root 13, because it's the same, the switch off from one function to the other is at the same place, to 2 of, what was that, the square root 2 minus x dx. I switched stylus sizes there, that's okay. So 2 times, well, x squared over 2 plus x evaluated at -1 and 9 minus root 13 plus, and I am starting a little bit to regret saying let's go ahead and continue because I really want to switch to the other method, but that's fine. So we have a substitution here, and after you've done these enough times, you might be able to say, oh, well, if u is 2 minus x, then du is negative dx. So I just have to borrow a minus sign. So that's what I'll do. So I'll put a minus sign out here, minus, apply the power rule, 2/3 times 2 minus x to the 3/2. Applying the power rule and the chain rule at the same time. In other words, integration by substitution. But I'm not writing it all out. From 9, to evaluate at 9 minus root 13 rather, and at 2. Okay. So now what I can do is, and I'm probably gonna run out of room. We'll make do. It'll be fine. So 2 times, well, it's gonna be 9 minus root 13 squared over 2 plus 9 minus root 13. I need an extra set of parentheses, double parentheses, minus 1/2 minus 1 minus 2/3. In fact, you know what? 0, right? When you evaluate that this function at the top end, 0, so that's convenient. So minus yeah, plus double negative. In fact, let's do it this way. Minus 2/3 2 minus 9 minus root 13 close 3/2 power open close. So I got 1 open, 2 open, 3 open, 4, 5. Okay, I think we're okay now. Oh, so 1, 2, 3, 4, 5, 6, 7 open total. 1, 2, 3, 4, 5, 6, 7. Okay, yeah, that should be good. All right. So giant messy number. we're not going to work out, what this is. It's simplified. Well, okay, you know what? I said we're not. Let's go ahead and do it. So let's distribute the 2. All right. So this gets a 2, this gets a 2, 2, this gets a 2, right? And then while I'm at it, I will distribute this minus sign and this minus sign. So this will be 9 minus root 13. I'll change that one later. Plus 18 minus 2 root 13. What is that? Plus 1, right? 1/2 minus 1 is negative 1/2. Double that's negative 1, but you're subtracting. Okay, plus 1. Plus 4/3 root 13 minus 7 to the 3/2. Okay, we'll call that good enough. That's as simplified as we're going to get it, right? And if we really wanted, we could get a decimal approximation to see, but how much is that? That's positive, of course, but is it a lot? Is it more than 5, less than 5? We can ballpark the area here. We could say, well, this is half a unit, so this is 1 unit, 2 units, 3 units, about 4, about 5. So we're looking at like 6, 6.5, something like that, right? That's what we would expect. But let's not do that right now. Maybe we'll do that in the next one. You can always throw that in a calculator yourself if you're curious to see. So that was a real pain, and these numbers are so messy. Can we do better? Well, let's redo this, and let's use, probably going to want to relist my functions here. Let's use a horizontally aligned rectangle, and maybe that will be a little bit better. I'm not guaranteeing it, I'm not promising anything, but I'm suspecting that it will be. Okay, so, oops, automatic rectangle, perhaps. Okay, so dy, that is the height, and I'm going to need to know what is that x coordinate is a function of y, and what is that x coordinate is a function of y, right? Well, for this one, there it is. I got it. That's how it was given to me, right? So 2 minus y squared. Hopefully I don't have to undo too much. 2. Basically, if I try to erase where I've highlighted, the highlight gets erased first before the stroke, so I don't want to do that. And this one, well, I need the x coordinate is a function of y. Okay, well, if I go back over here to my functions, take this guy, solve for x, y minus 1. Okay, not a big deal. So then the question is, where do I integrate from? Well, I'm going to end up doubling it later, so I'm not going to bother with the bottom half. I'm going to integrate starting at 0. If I slide my rectangle all the way to the axis, then my rectangle, sorry, I'm bumping into the microphone, I'll try to it's like right here, right? That's drawn really badly. The rectangle will be like right here at the bottom, right? And so the height level is 0. So we're going to integrate from 0 up to up here, right? So we are going to have to find some values for that, but we get the y coordinate, not the x coordinate. What is this y coordinate? We already worked it out. And I'm not going to do it all over again, but basically, it's this guy. Root 13 minus 1 over 2. Okay. So that's it. We are ready to get started. So integral, and there's only one of them. Change stylus size. Let's go with that. So integral from 0 to root 13 minus 1 over 2. It was minus 1, wasn't it? Yeah. Of, well, oh, I didn't label this. Sorry. This is sort of a straight thing, but that's fine. So the length, that's going to be 2 minus y squared minus y minus 1, right? So that's going to be 1 minus y squared, right? There's my length of my rectangle, and so the area would be that times dy. So the area is 1 minus y minus y squared dy. Okay. So one minus y squared dy. Okay, there we go. One integral. You are stuck with that messy number, but there's only one, so it's not so bad. So y minus y squared over 2 minus y cubed over 3, and from 0 to root 13 minus 1 over 2. So we're going to have root 13 minus 1 over 2 minus that squared, right? So that's going to be root 13 minus 1 squared over 8, if you work that out, minus root 13 minus 1 cubed over 24. There we go. Now this is pretty messy, and I'm not going to necessarily bother working out any simplification, right? I didn't have any minuses to distribute, and I wasn't. Oh, did I not double anything? Oh, I forgot to double it, didn't I? Yeah, okay. I forgot to double it. Well, that's easy enough, right? So root 13 minus 1 minus root 13 minus 1 squared over 4 minus root 13 minus 1 cubed over 12. There you go. And probably if you throw these, well, I would assume, I don't think we've made a mistake. If you throw this messy thing into a calculator and get a decimal, and go throw this messy thing into a calculator and get a decimal, it'll be, you get the same number, same result. Which one of these seems easier? Well, that's sort of subjective, right? To me, the bottom one was less work overall. I had to do less solving. My numbers were not too bad. I didn't have to do this right here. I didn't have to do this right here because I never needed x as a number. So I had to deal with arithmetic less. And so that's primarily because one of the equations we were given has x as a function of y rather than y as a function of x. That's one way, one clue that you might want to do a horizontally aligned rectangle rather than a vertically aligned rectangle. So that is that. I believe that's, yeah, we don't have any other examples that I prepared ahead of time. So this video is a little bit shorter than the last one, but that's okay. 70 minutes is fine. Anyway, the next video will be on 2.2, which I'm trying to remember what that is, but I guess you will see that when you see it.